One of the biggest questions physicists are striving to answer is what happened moments after the Big Bang. How the universe as we know it now evolved is a complex question involving study by vastly different branches of physics including particle physics, nuclear physics and cosmology. Now a team in the US has brought together the most recent advances in all of these disciplines to create a computer model simulating the first few minutes after the universe came into existence. A few seconds after the Big Bang, the universe was made of a thick, 10 billion degree cosmic soup of subatomic particles. As the hot universe expanded, the interactions of these particles caused the universe to behave like a cooling thermonuclear reactor. This reactor produced light nuclei, such as hydrogen, helium, and lithium, found in the universe today. The amount of the light nuclei created depends on what other particles, like neutrinos, were in the soup and how they interacted with each other. Neutrinos are very interesting. They're the second most abundant particle in the universe after photons, yet we still have much to learn about them, said Dr. Evan Gross, co-author of the study. By comparing our calculations with cosmological observables, such as the deuterium abundance, said Dr. Gross, we can use our burst computer code to test theories regarding neutrinos, along with other, even less understood, particles. It can be difficult to test these theories in terrestrial labs, so our work provides a window into an otherwise inaccessible area of physics. The model simulates conditions during the first few minutes of cosmological evolution to model the role of neutrinos, nuclei and other particles in shaping the early universe. It promises to open up new avenues for investigating existing puzzles of cosmology, said Los Alamos physicist Professor Mark Paris. These include the nature and origin of visible matter and the properties of the more mysterious dark matter and dark radiation. The frontiers of fundamental physics have traditionally been studied with particle colliders, such as the Large Hadron Collider at CERN, by smashing together subatomic particles at great energies, said Professor George Fuller, a physicist at the University of San Diego who collaborated with Professor Paris to develop the new theoretical model. The burst computer code allows physicists to exploit the early universe as a laboratory to study the effect of fundamental particles present in the early universe, Professor Paris said. Our new work in neutrino cosmology allows the study of the microscopic, quantum nature of fundamental particles, the basic, subatomic building blocks of nature, by simulating the universe at its largest, cosmological scale. The group said the work is important for nuclear data and could help in areas like nuclear energy, safety and security. The early universe is becoming such a tightly constrained environment with increasingly good measurements that we can test our descriptions of microscopic quantum physics, such as nuclear cross-sections, to high accuracy, added Professor Paris. This research has become possible only recently with the advent of astronomers' precision measurements of the amounts of nuclei present in the early universe. These measurements were made with very large telescopes, which are about 32 feet wide. The computer code has been developed in anticipation of the data that will be gathered by the next generation of extremely large telescopes. The telescopes, 98 feet across, are currently under construction. With coming improvements in cosmological observations, we expect our burst computer code to be useful for many years to come, said Professor Paris. The group is planning to improve the model to exploit the precision cosmological observations to reveal even more exotic physics such as the nature of dark matter and dark radiation. A complete understanding of dark matter, which comprises about a quarter of the mass in the universe, is currently lacking, Professor Paris said.